Spaceforge is a British aerospace company headquartered in Cardiff, Wales, with a mission that is rapidly redefining the boundaries of manufacturing by harnessing the unique conditions of space for advanced materials production. Founded in 2018 by aerospace engineers Joshua Western and Andrew Bacon, the company has pioneered orbital manufacturing technology aimed at producing semiconductor materials and other supermaterials that are extremely difficult to fabricate on Earth due to gravity, atmospheric contamination, and thermal variations. Spaceforge's core innovation lies in exploiting microgravity, ultra-high vacuum, and extreme temperature differentials in low Earth orbit to create, test, and refine materials with atomic structures that are orders of magnitude more precise and defect-free than those produced in terrestrial factories. Spaceforge's flagship orbital platform, named ForgeStar-1, comprises a compact, self-contained manufacturing satellite roughly the size of a large microwave oven. Designed to operate autonomously, ForgeStar-1 carries onboard high-temperature furnaces and experimental hardware configured to generate, contain, and control plasma and sustain temperature conditions necessary for semiconductor crystal growth. In late 2025, following its launch aboard a rideshare mission to low Earth orbit, ForgeStar-1 successfully activated its furnace and achieved temperatures approaching about 1,000 degrees Celsius, generating plasma in orbit for the first time. This demonstration represents a world-first achievement for any commercial spacecraft and validates that the extreme process environments needed for advanced crystal production can be created and managed in space without direct human presence. The success of this pilot mission has moved space-based semiconductor manufacturing from theoretical research to practical engineering reality and lays the foundation for future missions that will attempt actual material growth, return samples to Earth, and potentially transform global semiconductor supply chains. The environmental conditions present in low Earth orbit confer manufacturing advantages that simply cannot be replicated on Earth, and these advantages are central to Spaceforge's vision for semiconductor production. On Earth, gravity induces convection currents in molten materials, which can introduce defects, impurities, and stresses into crystal structures during fabrication. In contrast, the microgravity environment in orbit essentially eliminates buoyancy-driven convection, allowing atoms within a molten material to settle and bond in highly uniform and ordered arrangements. This effect enables the formation of crystals with far fewer structural defects, which is a critical factor for semiconductor performance because even microscopic irregularities can dramatically impact electrical properties. In addition, the vacuum of space provides an ultra-clean environment with negligible contamination by atmospheric gases such as nitrogen and oxygen, which can interfere with crystal growth and introduce impurities into semiconductor materials. Terrestrial vacuum chambers attempt to replicate this, but they are limited by residual gases and the physical constraints of ground-based systems. The combination of microgravity and near-perfect vacuum in orbit, therefore, allows for the production of materials with atomic ordering and purity that may exceed what is feasible on Earth. Furthermore, the absence of an atmospheric buffer and gravitationally induced heat transfer in space means that thermal gradients can be controlled with exceptional precision, enabling more stable high-temperature processes, such as plasma-assisted growth and other gas-phase crystal formation techniques. Spaceforge's ForgeStar-1 satellite has taken advantage of these environmental conditions by generating and stabilizing plasma at about 1,000 degrees Celsius, demonstrating that the processes necessary for advanced semiconductor manufacturing can be carried out in orbit. These natural advantages of space thus form the technological bedrock of why orbital semiconductor production could one day produce materials that outperform traditional Earth-made semiconductors in efficiency, defect density, and reliability. The ForgeStar-1 mission marks a significant milestone in the history of space manufacturing, representing the first commercial attempt to operate semiconductor production processes in orbit. Launched to low Earth orbit aboard a dedicated rideshare mission in mid-2025, ForgeStar-1 is a compact, autonomous satellite designed to test and validate essential manufacturing technologies in space. Its primary objective has been to demonstrate that controlled plasma, a superheated gas required for certain crystal growth processes, can be created and sustained in the microgravity environment of space. In December of that year, mission controllers successfully powered up the satellite's onboard furnace, achieving temperatures of approximately 1,000 degrees Celsius, and generated plasma, thereby proving that the hardware and software systems can withstand and operate under the extreme thermal and vacuum conditions of space. This plasma generation was not intended to produce finished semiconductor materials. Instead, it was a foundational experiment to confirm that the core physical conditions required for gas phase crystal growth and other high-temperature manufacturing processes can be reliably produced and monitored in orbit. Engineers will now conduct systematic tests to observe how plasma behaves in the absence of gravity, collecting data that will inform the design of future missions aimed at producing actual semiconductor crystals. The Forge Star, one demonstration, has been widely recognized by space and semiconductor industry analysts as the first time a commercial satellite has purposefully generated and controlled the manufacturing environments needed for advanced semiconductor materials in orbit. With this demonstration complete, Space Forge has a roadmap towards significantly larger satellites, eventual material production, and sample return technologies that could one day allow space-grown semiconductor precursors to be delivered back to Earth for integration into global supply chains. The development of orbital manufacturing technology by Space Forge has been underpinned by substantial financial backing, strategic partnerships, and growing interest from both commercial and government sectors. In mid-2025, Space Forge announced the successful completion of a series of funding round totaling approximately £22.6 million, the largest such funding round ever secured by a UK space technology company at that stage. This investment was led by the NATO Innovation Fund, with significant contributions from international partners including the World Fund, the National Security Strategic Investment Fund, and the British Business Bank, among others. The funding serves multiple purposes, including accelerating development of Forge Star 2, Space Forge's next-generation satellite, designed not only to continue in-orbit manufacturing experiments, but also to test technologies for returning fabricated materials safely to Earth. The investor interest reflects the broader recognition that space offers a compelling new frontier for producing next-generation materials that could transform key industries, including advanced computing, telecommunications, clean energy infrastructure, and defense technologies. Analysts have noted that space-manufactured semiconductor materials could theoretically reduce energy consumption and defect densities compared with Earth-made equivalents, potentially improving performance in data centers, electric vehicle charging systems, and microelectronics. The strategic investment by defense and innovation funds also underscores the geopolitical importance of resilient and advanced material supply chains, particularly in an era where semiconductor access and capabilities are viewed as critical national assets. Through these funding and partnership efforts, Space Forge is positioning itself at the forefront of a nascent but rapidly evolving sector that seeks to leverage the unique physical conditions of space to enhance material quality and performance in ways that are difficult or impossible to achieve on Earth alone. Looking forward, Space Forge's pioneering work lays the groundwork for a new paradigm in how semiconductors and other high-value materials might be manufactured and integrated into Earth's technology infrastructure. While the Forge Star, one mission has focused on demonstrating the core physical processes needed for space manufacturing, subsequent missions are expected to expand into actual material growth, refinement, and return technologies. Future orbital factories are planned to be significantly larger and capable of producing the quantities of ultra-pure materials needed to support thousands of semiconductor chips, rather than just experimental samples. A critical next step will be the deployment of heat shield and reentry systems that can safely bring manufactured materials back through Earth's atmosphere without damage, enabling space-grown components to be inspected, tested, and ultimately used in commercial products. As this technology matures, it could yield fundamental changes in global supply chains for advanced electronics by supplementing or enhancing terrestrial manufacturing with materials produced under the exceptionally clean and controlled conditions found only in space. In the long term, space-based manufacturing could support a range of industries beyond semiconductors, including quantum computing, superconductors, optical systems, and even pharmaceuticals, as research shows that microgravity environments can lead to improved crystal quality across diverse applications. Moreover, the success of space manufacturing initiatives like Space Forge's could encourage new regulations, international collaborations, and investment frameworks to ensure these technologies benefit global economies responsibly and sustainably. While significant engineering, economic, and logistical challenges remain, the achievements to date, including the world's first commercial plasma production in orbit and major investment milestones, suggests that orbital semiconductor manufacturing is no longer theoretical, but a growing reality that could reshape the landscape of high-technology production in the 21st century.